this video, I am going to find the inverse Laplace transformation of this function. This is a good example when the poles of our function is a combination of real and complex numbers. So to find the inverse Laplace transformation, the first step, we have to set our denominator equal to 0. So we have to set s cubed plus 2s squared plus 10s equal to 0. We can simplify this as s times s squared plus 2s plus 10 equal to 0. So one of our poles is a real number, s equal to 0, and right here for this portion, we are going to have s2, s3 will be minus 2 plus or minus of the square root of 4 minus 40 divided by 2. So this will be equal to minus 2 plus or minus 3j divided by 2. So this will be equal to 6j divided by 2. So this will be equal to minus 1 plus or minus 3j. So we have a real number pole, which is s equal to 0, and a complex number, which is that. So for the real portion, we know that the constant associated with our pole will be equal to the limit as s approaches to our pole of s minus p multiplied by fs. So this will be equal to the limit as s approaches to 0, or pole is 0, of s minus p, which is s minus 0 is s multiplied by fs, and our fs is multiplied by 2s minus 8 divided by s multiplied by s squared plus 2s plus 10. So this s will cancel out, and as s approaches to 0, this portion will be 0, this portion will be 0, and that portion will be 0. So our constant associated with our pole 0 will be minus 8 divided by 10, or is minus 0.8. So our original function associated with our real pole f of t will be equal to our constant associated with our pole 0 multiplied by e to power our pole times t. So this is equal to minus 0.8 multiplied by e to power 0t, which e to power 0t is equal to 1. So our original function associated with our real pole will be minus 0.8. Now we have to find our f of t associated with the complex number. So for that reason, we know that we can factor out. So this can be written as s multiplied by, we can factor out s squared plus 2s plus 10 as s plus 1 square plus 3 square. So we can write down fs like that. And now we have to find the term ps in this relationship. ps is equal to s plus 1 square plus 3 square multiplied by fs. So our function associated with our real pole will be equal to minus 0.8 plus other term. By other term, I mean the function associated with our complex number, then we just added into that. So we find ps in this relation, this multiplied by fs, which fs is 2s minus 8 divided by s multiplied by s plus 1 square plus 3 square. So here, these two terms will cancel out. So our ps will be 2s minus 8 divided by s. Now we have to find our p minus 1 plus j3, which will be equal to 2 times minus 1 plus j3 minus 8 divided by minus 1 plus j3. So this will be equal to, so this will be equal to 2 times minus 1 will be minus 2 plus j6 minus 8 divided by minus 1 plus j3. So this will be equal to minus 10 plus j6 divided by minus 1 plus j3. So once we find that our function associated with our complex number will be equal to the magnitude of p minus 1 plus j3 divided by b multiplied by e to power minus t sine of bt minus at, this is a and b, sine of bt plus the argument of p minus 1 plus j3. So now that we have p minus 1 plus j3, let's first find the magnitude of that. So the magnitude of p minus 1 plus j3 will be equal to the magnitude of the top, which is the square root of 10 square plus 6 square divided by the square root of 1 square plus 3 square. So this will be equal to the square root of 136 divided by the square root of 10. So this is our magnitude of P1, P minus 1 plus J3. Now let's also find the argument of P minus 1 plus J3. So the argument of P minus 1 plus J3 will be equal to the argument of minus 10 plus J6 divided by minus 1 plus J3, which this will be equal to the argument of minus 10 plus J6 minus the argument of minus 1 plus J3. So now the argument of minus 1, this will be tangent inverse of 6 divided by minus 10 minus tangent inverse of 3 divided by minus 1. So if we assume that this is our real axis and this is our imaginary axis, this is our imaginary axis J. So here we have minus 10 plus 6. 1, 2, 3, 4, 5, 6. This is 6. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have this vector, and here we have minus 1 plus J3. Minus 1, this is minus 10, plus J3. Minus 1, sorry, right here. So we will have this. So let's find the tangent inverse of 6 divided by minus 10. So that would be that would be 0.6. Inverse tangent of 4.6, which is 30.96 degree from this axis. So this minus 180. So we are saying this 149 degree from here to here will be 149 degree, and the tangent inverse of 3 minus 3 will be 3. Tangent inverse of that will be 71.56 from the imaginary axis. Minus 180 will be 108 degree. So this will be 108 degree. So this angle here will be 140 minus 108. 140 minus 108. So this will be sorry, let me see, 6.6 inverse tangent of minus 180. This is 149. Sorry, this is 149 degree. So 149 degree minus 108. So this angle here will be 41 degree. So the magnitude of P minus 1 plus J3 is this, and the argument of P minus 1 plus J3 is 41 degree. Is 41 degree. So let's go ahead. So this is. So let's go ahead and plug that into this formula. So our FAT associated with our complex number, will be equal to magnitude, which is 136 divided square root of 136 divided by square root of 10 divided by B. Our B is 3 multiplied by 3 e to power minus t sine of bt, or b is 3 sine of 3t sine of 3t plus 41 degree. So this is our function associated with our complex number. So our plus other term. So our complete formula for our function will be minus 0.8, which this is associated with our real number, plus this, plus the square root of 136 divided by 3 square root of 10 e to power minus t sine of 3t plus 41 degree. So this is the answer. This is the answer. This is the inverse Laplace transformation of that function. And I have had a couple requests that both of them are very good examples. In next two videos, I will solve those two requests first, and then we move into some problems, some engineering problems. See you later.